Hi, welcome to another Algebra 1 video. In this video we will look at section 2.6, which is about absolute value inequalities. Section 2.6 is also the last section of chapter 2. In this video we will learn about properties of absolute value inequalities, solving and graphing inequalities on a number line. And finally, we will also learn how to solve some special cases that arrive when you solve some absolute value inequalities. So what are absolute value inequalities? Before I talk about inequalities involving absolute value expressions, let's do a recap on what the term absolute value even means. Absolute value is an expression in mathematics which determines the distance or the absolute value of some number from zero. In chapter 1 we learned about absolute value, and the notation for absolute value is something that looks like this. You have two bars and you have some variable or some number in it. So say you take the absolute value of -5. We know that the absolute value of some number or some expression is the distance of that expression or number from zero. If we look at the number line, we can see that -5 is a distance of 5 from 0. So the absolute value of -5 would equal to +5. And absolute value is always positive. That's another property of absolute values. In chapter 1 we also learned about absolute value equations, which are similar to absolute value inequalities. An absolute value equation is an equation in which the term absolute value is present. So you could say the absolute value of 2x is equal to 0. Since we have the expression 2x equals to another expression 0, we can say that this is an absolute value equation. Another example of an absolute value equation could be x is equal to 5. But how do you solve this absolute value equation? Well, we have to know the properties for that, which we talked about in chapter 1. We know that the absolute value of some variable or some number, when it equals to some other number c, then the absolute value of that number equaling to c can be given by two solutions giving x equals to c and x equals to the reverse of c, which is -c. So in this case, when we solve the absolute value of x equals to 5, we get that x equals to -5 and x equals to +5, because we have a positive value for the number here and a negative value. But what about an absolute value inequality? We know that an absolute value inequality, from its term, is an inequality which consists of an absolute value. So you could say that the absolute value of x plus 3 could be less than or equal to +3. That's an absolute value inequality. Another example could be the absolute value of -2x is greater than 0. That's also an inequality. But to solve these inequalities, we have to know some properties specific to inequalities, as there's some difference compared to solving equations that have absolute value terms. So let's say that you have the inequality, the absolute value of ax plus b is less than c. In this case, I can see that I have an inequality sign equaling to some number that we don't know, which is c. To solve these inequalities, we have to make sure that the variable is not a negative number, or else you can't solve the inequality. So what would this inequality equal to when you solve it? Similar to compound inequalities, which I covered in section 2.5, you get that this absolute value inequality equals to ax plus b is less than c. So one of the inequalities is the same as the original inequality, but then you get ax plus b is greater than -c. So like equations, like absolute value equations, when you flip the sign of that number, you have to change the inequality sign, because when you multiply or divide by a negative number in inequalities, you have to change the sign. This property also applies to signs like less than or equal to. Now, what about this inequality? We're given that the absolute value of ax plus b is greater than c. In this case, just like the previous example, we get exactly the same inequality without the absolute value. So our first solution would be given by ax plus b is greater than c, which is the same as this. And the second solution is given by flipping the inequality sign. So we had greater than, but now we have less than. And then we multiply the c by a negative number. Again, this property also applies to the sign of greater than or equal to. Now let's solve some absolute value inequalities. So in this first question, we're given that the absolute value of x is less than or equal to 3.5. Well, from this sign, we know that this property is going to apply, the first one. So this would give us that the absolute value of x is less than or equal to 3.5. So the first equation is identical, and then we get the second equation, which is x is greater than or equal to -3.5, because we flipped the sign and now we also have to flip the inequality sign. And the equation is solved. We're given that the answer for the absolute value of x is less than or equal to 3.5 is that x has to be less than or equal to 3.5 and it has to be greater than or equal to negative 3.5. So let's graph this inequality on a number line. From the solutions, I know that my two critical numbers are positive 3.5 and negative 3.5. I know that my first inequality says that x has to be less than or equal to 3.5. Since it has an equal sign, we're gonna place a closed circle, and since it's less than 3.5, we can extend this line in this direction. We're also given that x has to be greater than or equal to negative 3.5. Well, since it's an equal sign, we place a closed circle, and since it's greater than negative 3.5, we extend the ray in the rightwards direction, as the positive numbers are in this direction. Well, here we can see that we have an overlap that's happening. So our solution is an intersection, or an AND solution. So our solution says that our x values are from negative 3.5 to 3.5. Here I have another inequality which says that the absolute value of x plus 1 is greater than 5. From this sign, I know that we're going to apply the second property. So we get that x plus 1 is greater than 5, which is the same as the first inequality. And the second inequality will be an OR inequality, which will give us x plus 1 is less than negative 5. So we have flipped the sign for the 5, so we get negative 5, and therefore we also flip the inequality sign. Now, just like inequalities, we can solve these two inequalities. So here I can subtract 1 from each side, and I get that x is greater than 4. Or from here I can subtract 1 again from each side, and I get that x is less than negative 6. So let's graph these two inequalities on a number line. I know that the two of my critical points are 4 and negative 6. So I can plot 4 over here and negative 6 over here. And since both have no equal sign in their inequality signs, they're both going to be an open circle. And now the inequality says that x has to be greater than 4, so we can extend the ray in the rightwards direction, as numbers that are greater than 4 for x are in the rightwards direction. And here we're given that x is less than negative 6, so we can extend the ray in the leftwards direction, as numbers that are less than negative 6 are in the negative direction. Now here's another property which I didn't mention over here, and that is when you have an inequality in which you have a less than or equal to sign, it happens for the most part you'll end up with an intersection. And that is because it's a compound inequality for the solutions in which you get an AND constraint. While when you have greater than or equal to for your inequality sign in an absolute value inequality, it turns out that your solutions will be in the opposite directions and there will be no intersection, but it will be a union, which is why it's an OR inequality. In number 4, we're given that 2 times the absolute value of d plus 1 minus 7 is greater than or equal to negative 1. So in this absolute value inequality, I see that I can add 7 on each side of the inequality. So by doing so, I get the negative 7 and the plus 7 cancelled out, leaving us with 2 times the absolute value of d plus 1 is greater than or equal to negative 1 plus 7. And if we calculate that, we get positive 6. And now from each side of the inequality, I can divide by 2. And so 6 over 2 gives us 3, and here we're left with d plus 1, and the absolute value is greater than or equal to 3. And by now, I think you know that we can use this property to get d plus 1 is greater than or equal to 3. And since it's greater than or equal to 3, it's going to be an OR inequality. So our second inequality would be d plus 1 is less than or equal to negative 3. And then we just solve these two inequalities like a regular inequality. So we get d is greater than or equal to 3 minus 1, which gives us 2. Or d is less than or equal to negative 3 minus 1, which gives us d is less than or equal to negative 4. So this is our compound inequality. Now let's graph it on a number line. I know that my two critical points in this inequality solution are positive 2 and negative 4. So I can mark them here. And then we're given that d is less than or equal to negative 4. So I can place a closed circle and extend it to the negative direction because it says that d is less than or equal to negative 4. And for d is greater than or equal to 2, I can place a closed circle again because there's an equal sign and extend the ray to the positive direction or greater than 2. Now let's look at special cases when you solve absolute value inequalities. Instead of revealing the cases, I'll solve some inequalities which have the cases involved, so you can get a better understanding of how those cases arrive. In this inequality, we're given that the absolute value of x plus 3 plus 1 is less than negative 5. So I can subtract each side of the inequality by 1, and by doing so, we're left with x, the absolute value of x plus 3 is less than minus 5 minus 1, which gives us minus 6. Well, here I see that I can't have an absolute value that is less than some negative number. In fact, an absolute value solution cannot be a negative number, so there's no solution to this inequality. And if you graph it on a number line, you'd plot nothing on the number line. Let's look at a second case. In this inequality, we're given that the absolute value of n plus 2 minus 3 is greater than or equal to negative 6. So here I see that I can add 3 on each side of the inequality, and this simplifies to the absolute value of n plus 2. This cancels out and we're left with n plus 2 is greater than or equal to negative 6 plus 3, which equals to negative 3. In this inequality, we're saying that n plus 2 in its absolute value expression can be greater than or equal to negative 3. This is true because the absolute value of an expression will always be a positive number, so it has to be greater than or equal to negative 3. And therefore, this inequality has infinitely many solutions. So all real numbers on the number line will prove to be the solution for this absolute value inequality. So on a number line, if we graph it, we'll get that all real numbers are the solution to n in this inequality. And this is it for section 2.6 and chapter 2. I hope you found this video helpful and you understood the concepts of absolute value inequalities and how they differ a little bit with absolute value equations. Leave a comment in the comment section and provide feedback so I can improve my videos in the future. And I'll see you in the next video. Thanks for watching.